Second part of the lecture today, we will start with an example still on the subject of viscosity, and then we will move on to some other aspects of fluid behavior. So in this example, again, I will post this on Blackboard, so you don't have to write down everything, but do write, you can write down the minimum information you need to solve the problem. We have a velocity distribution between two parallel plates as shown here in the diagram. And this is the velocity distribution. In other words, we have a parabolic velocity profile as I have drawn in this sketch. And the velocity V is the average velocity given. In this case, we're going to work not with the metric system, but we're going to work with the British system of units, 2 feet per second. Also, we're going to have a measure of the width of this channel between the two parallel plates. We have h on each side of the center line, and h is equal to 0.2 inches. And finally, the Newtonian fluid has a given viscosity of 0.04 pounds second divided by feet squared. So the questions are, first, find the shearing stress acting on the bottom. So the first question is shear stress at the wall, bottom wall. And question number 2B is find the shear stress acting at the center line. So write down your minimal information there to try to solve this problem. From the center line, yes. Okay, let's try it. Let's try it together. So, well, they say it's did it say this? If it didn't say it had to say that it's a Newtonian fluid, and so we have the following relation, which is tau equals mu du dy. So our first step is going to be to get du dy from the given parabolic velocity distribution. So let's get the velocity gradient. Du dy is equal to, well, the first term is not a function of y, the second term has a minus sign, and we have 3, and this is going to be 2y, so the 2 cancels out. So we have, oh, I forgot the v, let's keep the v in there. And, well, I don't need to write the 2's, right? You can follow that, the 2 cancels out. Y divided by h squared. H squared, remember? Yeah. Classic little gotcha moment there if you forget the h squared. And how do you make sure? If you take just a small moment to inspect that the dimensions are correct. And you would have remembered, and you would have noticed that you had something missing, you would have gone back and caught the h squared. So we now want to find tau at the bottom wall, where y is equal to minus h. So we have our coordinate system at the center line. So du dy is 3v divided by h. And here you would have seen immediately, right, if you had forgotten the h, that here you have velocity length. And if you had forgotten the h squared here, you would have noticed something really amiss there. You have a question? Why this negative sign or this one? The second one? Okay, so we've made a coordinate system where y is here and x is here, and maybe I forgot to indicate that, but I had indicated that you had h here and h here, and so this is, with respect to this coordinate system, this distribution of velocity applies. Yes, another question. Yes, 0 is because of my choice of coordinate system there. The center line is 0. Everyone with me up to here? Good. So now we have the UDH, and now we can insert the values to get the stress, right? So now we can let's insert the values to get tau. Tau is mu du dy. Okay, so let's put the values. Now, when I put the values here, what we had a tip for doing better on exams from last class is to carry over our units, and so we're going to do that here. And we're going to write 0.04 is the value of viscosity, pound second divided feet squared, and we had just a numeral 3, and we have velocity, which is 2 feet per second, and in the denominator we have well, h, right? Just h. And h is 0.2 inches. And here we notice that we have feet at the top, so we have to make a conversion. So we're going to use the grid method to convert to feet. 1 foot is how many inches? 12 inches. So this guy here is just multiplying, we're just multiplying by 1. 1 foot is equal to 12 inches. But by applying this in sort of shorthand application of the grid method that we discussed last class, we can make immediately the conversion of units that we need to make here so that everything is consistent. So now you can see that the units are consistent. We have this feet, and second, and we get basically the second goes away, this feet goes away, these inches go away, and the only thing I'm left with is pounds per square foot, which is correct units for stress or pressure, right? We can put our numbers now on the calculator, including all of the given numbers and also this 12 that comes from the conversion, of course, and we get 14.4 pounds per feet squared. Okay, did you have a question? I thought you had a question. No, you're fine now? Okay. So this is our shear stress, and it's a force per unit area, and therefore it has a direction. So normally you would want to say that this is in the direction of flow. And the second question was to find the shear stress at the center line. The center line is y equal to 0. And so if we go back to our equation, at y equal to 0, du dy basically is going to be equal to 0. Yes, so du dy is equal to 0, and therefore tau is equal to 0. So what we have here is that, and this is a classic result for a parabolic velocity profile. You have a linearly varying stress, shear stress, that goes from 0 at the center line to a maximum value at the walls. And so what this looks like, if I want to make a plot of the shear stress, in this case with respect to y, I'm going to have at y equal to 0, the center line, a value of stress of 0, and a maximum at the wall, forgive the crooked lines, and this will be minus h and h, and we have a linear variation of the shear stress. This is a classic result for parabolic velocity profile. Yes?
Which direction is u on each of the walls?
U was, is a little bit crooked, but it was a parabolic velocity profile like that, and in that same direction is the force. Let's see, at the wall. Okay, so let's go on to the next section of the course. We're going to discuss now compressibility effects, the compressibility of fluids. I have a couple of definitions first that we need. The first one is the bulk modulus. The bulk modulus measures the fluid's resistance to a uniform compression. So like shown in that little cartoon here, we imagine a small element of fluid and we apply a compression, a normal force. Up to now we were discussing tangential forces and the relationship of tangential forces with viscosity, which was the resistance of the fluid to those tangential forces. Now we're looking at the normal, the perpendicular forces, pressure, a compression, and we have a property of the fluid which is the resistance to such forces. This is called the bulk modulus. So it is the pressure increase needed to cause a relative decrease in volume. So, depending on the choice of nomenclature, one of the nomenclatures is E sub V here for the bulk modulus, and it's a change in pressure required to produce a relative change in volume. So dV divided by some original V. So it's a relative change in volume. And we can rewrite this as V, this capital V is volume for dP dV. That's the bulk modulus. Now notice the negative sign. Think about it a little bit. Why is there a negative sign there? Sorry? Because, of course, when you apply a positive pressure, what happens to the volume? It decreases, right? A positive pressure will make the volume decrease. And so dV will be negative for a positive dP. Good. That's the negative sign. Okay, so dimensions are the same as pressure. And the reason is that this is a relative change in volume, so dV over V doesn't have dimensions. So we have force divided by length squared. And so the units are in metric Pascal, which is Newton divided by meter squared, and in the British gravitational system, pounds per square inch. And one thing to note is that liquids are nearly incompressible. Which means that their value of the bulk modulus is very large. For example, water. The bulk modulus of water is equal to 2.15 times 10 to the 9 Pascal. Now what this means is that you need a pressure of about 200 atmospheres for a 1% change of volume. Okay? So, and there is an alternative expression also for bulk modulus using m equals rho times v. So v equals m divided by rho, and therefore dV is equal to minus m divided by rho squared d rho, or minus v over rho d rho. So now we can write the bulk modulus in terms of the density rather than the volume, and we get EV is equal to rho dP d rho. So compression of liquids is not very interesting, you can see, because of the very large bulk modulus, nothing really happens. You have to, apply incredible amounts of pressure to do anything with it. But compression of gases is quite interesting. It's much more interesting. For gases, you can, there's also a whole branch of fluid mechanics that studies the compressible flow, the compressibility of gases. And you have to bring in a lot of thermodynamics in that case. The compressibility phenomenon depends very much on how the process is applied, how the process of applying pressure. The negative went away because we had, sorry, I just erased my annotations under ephemeral. I can't really record them. They're recorded in the movie, but no. So you had a minus dV d rho equals minus rho over, because you have 1 over rho, and so I'm taking the derivative of 1 over rho to the minus 1. So there's the minus sign. And that one carried all the way down, and then when we made the replacement, it took away the rho of the original equation. Sorry, it took away the minus of the original equation. So I was saying that compression of gases depends on the type of process that we have. Depends quite strongly, in fact. On the type of process. So we have isothermal or isentropic. The isothermal process, well, takes place under conditions of constant temperature. And for isentropic process takes place under conditions of no friction and no heat exchange. Basically a reversible process with no dissipation. In the case of the isothermal process, so I said you have to bring in a little bit of your thermodynamics and recall for this case the ideal gas law. And let me take a moment here to stress that it's the ideal gas law, so you don't apply it in water. And the reason I mention this, although it sounds obvious, is because indeed a student a couple of years ago did apply it in an exam to water, which caused me a tremendous amount of consternation for a moment there. So I don't want that. I want to see that again. The ideal gas law applies only to gases. Make sure you never apply it to in that case it was, I think, a Venturi pipe with some water in it. Not a good idea. Rho equals P over RT. Here's our ideal gas law, where P is, of course, the pressure, and for the isothermal case, we have then that P over rho equals to a constant. In the case of the isentropic compression, we have a relation like P over rho, but with an exponent equals to a constant. Where this exponent K is the ratio between the specific heats, Cp over Cv, where Cp is the specific heat at constant pressure, Cv is the specific heat at constant volume. And generally, this is about as much of thermodynamics that we're going to need in this course. And we are going to use this specifically for the case of gases, because gases are highly compressible, and therefore we need to pay attention to the process, the thermal process. So, for example, for water, now what do I have here? Air. Water, of course, is incompressible. The ratio is 1.4. This is one of those numbers that you kind of need to memorize, okay? Very quickly, 1.4. Many of you are taking thermodynamics concurrently with this course, but as I said, this is about as much thermodynamics as you need. So, it should be okay. And what did we say last class? What was another tip that we had for doing better on exams? That had to do with the ideal gas law. Very good. Always use absolute temperature and absolute pressure in your in general in your thermodynamic equations. So Okay? I had some numbers on that in those equations, which now I don't, so revise this note. So forget about those numbers there. I didn't. From the previous two equations that we had, which were for ideal gas law, rho equals P over RT, and our isentropic process. With those two equations, we can get the bulk modulus for gases which are being compressed with either one of those processes. And so for the case of an isothermal process, where we have P over rho equals constant, and remember our bulk modulus is rho times dp d rho. And in this case, for the isothermal case, combining, basically obtaining the derivative, we want to obtain the derivative by looking at the derivative dp d rho. Then we can write for our bulk modulus for the two processes, isothermal and isentropic. The bulk modulus, in this case, is Kp. So, for example, some numbers for reference. At atmospheric pressure, standard atmospheric pressure of 101 kilopascal, or 101 times 10 to the 3 Pascal, then with the value of the ratio between the specific heats for air, which is 1.4, then the isentropic bulk modulus of air at standard conditions is, just multiply those two numbers and we get 141.4 kilopascal. Now remember, we just had in the previous slide the case of water. So for water, we had a bulk modulus equal to 2.15 times 10 to the 9 Pascal. So this is about 15,000 times larger, which indicates really how different gases are from liquids. It's an enormous difference in terms of their behavior. Bulk modulus of water is 15,000 times bigger. So gases can only be treated as incompressible in very particular situations, and these are when pressure changes are small. How small? Small, well, small is a relative term, right? It needs to be in comparison to something. And this something is the speed of sound. I'll give you a second to write for those who are taking notes. Okay. So, the speed of sound. Sound is really a vibration. It's a small disturbance which is traveling through the air. That is sound. And I think the best illustration of what a sound wave looks like is a slinky. The illustration that I like the best of a traveling wave. Sort of like a spring, perhaps, that you have, and you squeeze, and that disturbance travels along the spring, like in that cartoon on the slide. That's the traveling wave, a model of a traveling wave, and that's sort of what sound is, a vibration. Like you see here in the spring cartoon, we cause a little compression, and that disturbance, that compression travels along. And that is exactly what happens with sound. It's a small compression that travels as a wave. This traveling disturbance is a wave. Sound is a wave. It behaves like a wave. And this is our model. So the velocity at which the small disturbances travel is the speed of sound. I think this disappears, yes. Usually we use the letter C, and it is obtained from the equation C is equal to square root of dp d rho. Or in terms of the bulk modulus, C is equal to square root of bulk modulus divided by rho. Now, notice that, well, I didn't say here, but I should have said that in fact it is a small vibration. And it's so small that really there is negligible heat transfer, and so the process is isentropic. So that means we use the isentropic bulk modulus, and so I can write here for the bulk modulus K times P, and so we have that C is equal, the speed of sound is equal to square root of C times P, K times P over rho. And for ideal gases, then we have that C is equal to square root of KRT. For example, air has a speed of sound equal to 340 meters per second at standard conditions of 15 degrees Celsius, which is about 288 Kelvin. And of course the definition of the Mach number is the ratio of the velocity of a flow with respect to the speed of sound. more important property that we're going to discuss today is the vapor pressure. Now, of course, you know by observation that liquids evaporate when they are left in contact with the atmosphere. And basically what happens there is that liquid molecules at the surface, when they have enough momentum, they're able to escape the surface. Over time, enough molecules are able to escape the surface that you can see a volume of, say, water evaporate, or you observe the rain in the streets after a while drying out, and so on. So all liquids in contact with the atmosphere evaporate. So this is an experimental observation. And the engineering concept that is involved with that is vapor pressure. Vapor pressure is the pressure of a vapor when it is in equilibrium with its own vapor phase. Sorry, with the liquid and the liquid and the vapor phase in equilibrium. The two phases in equilibrium. Basically what we're saying is the number of molecules leaving the surface by evaporation is the same as the number of molecules returning to the liquid, and so there is no change there. This is a function of temperature. And of course you've observed the process of boiling. Boiling occurs when the vapor pressure equals the ambient atmospheric pressure. That's the process of boiling. But of course it depends on, since the vapor pressure depends on temperature, then the boiling point also depends on temperature. That's going to be the pressure. So at a given pressure, if the pressure doesn't change, the atmospheric pressure doesn't change, we need to change the vapor pressure of the liquid by raising the temperature until they're equal, and then boiling will happen. Boiling is induced, as you know, by raising the temperature. And at a given temperature, boiling can be induced by lowering the pressure. So this leads to a very important phenomenon for mechanical engineers and for many other fields of engineering as well. When you have a flow, say of water, and in this flow the pressure falls below the vapor pressure of the fluid, you will have boiling. You will have spontaneous evaporation of the liquid phase. And this can happen in pipes, in the water. You may remember from a first class seeing the bubbles being released behind a propeller. What happens there is the fluid is being sped up to such a velocity that, due to another effect that we're going to discuss later, the pressure is reduced, and once the pressure is reduced below the point of the vapor pressure, we get spontaneous evaporation of the fluid. This is a process called cavitation. Cavitation is when the pressure falls in a fluid such that the vapor pressure is reached. And basically what happened is that bubbles form spontaneously in the flow. Now, as the bubbles move along to other areas of the fluid where there is a larger pressure, they collapse. And when they collapse, there is an effect that their shape changes in such a way that they produce a high-speed jet that can damage materials hard as steel. Let me show you. First of all, here is another effect actually. That sound is generated by the bubbles. Cavitation is observed here by those bubbles. What happened in this movie is that water was flowing in this direction, and the velocity of the water is changing. And as it changes, it is, when it accelerates around this bend, the pressure drops below vapor pressure, the bubbles are formed, and the bubbles can produce that sound. So you can hear, and many engineers have a trained ear to hear when cavitation happens in some devices or pipes and so on. It's very sought after skill. So let me show you some examples of cavitation that you saw in a video before in the first lecture. The bubbles here are being caused by the water. This is not air. It's steam, basically. It's water vapor. The bubbles are water vapor that is being formed by the pressure in the fluid decreasing below the vapor pressure. And what this can cause is this sort of damage. So you can see how important this can be for engineering applications. All of this is cavitation damage on the propeller. And therefore designing propellers and so on to minimize cavitation, determining the right speeds of operation so that you can avoid cavitation and so on are going to be very important problems to solve as engineers if you are involved in this field of doing propellers. And I have here an explanation of what happens in just this cartoon. This one above here is an actual picture that was captured, and a very famous picture indeed, because it captures right the moment when this jet is created. What is happening is that the bubble was created at one point of low pressure, where the vapor pressure was reached. The liquid evaporated, it formed bubbles. Then the bubble moves to an area of higher pressure. So here you see the higher pressure squeezing the bubble in. The bubble buckles like you would, when you stand on a can of fluid. If it has a little wrinkle, you stand on it, there's a point where it just buckles. So the surface of the bubble buckles, sort of with the effect of the pressure. Oops, let me go back to that. And this, in turn, produces, in the end, this high-speed jet. And when this collapse of the bubble happens nearby any surface, this jet can erode the material and produce the damage that I showed you in the previous picture. It is quite a very important phenomenon. Now, when uncontrolled, this cavitation, you can see that is very damaging. However, clever engineers have found some ways to use this in a controlled way for certain applications. So cavitation actually has some non-destructive applications. For example, in chemical engineering, the cavitation and subsequent collapse of the bubbles, the whole process, can be used to mix, to homogenize, or break down suspended particles. It is also used for water purification. The bubbles and their collapse produce very high speed jets that can break down certain contaminants in the water, break down recalcitrant material. And biomedical applications are very interesting, and in fact there are several people in this university that work in research in this area, biomedical applications. The destruction of kidney stones by the process that's called lithotripsy. I'm not sure if I pronounced that correctly. Lithotripsy maybe is the proper way to pronounce. So it is actually used to destroy kidney stones. The bubbles are controlled, created, and they collapse near the kidney stone, and the kidney stone basically there's a shockwave and it's destroyed. It is also under research for the destruction of cancer cells, a very controlled application of what's called a high-intensity focused ultrasound, and cavitation plays a role in this process to destroy cancer cells. And there are other industrial applications, for example, for cleaning, where it can be used for loosening contaminants. But let me show you this one last video before you go.
Far from being quiet, the ocean is filled with a cacophony of animal noise that can even disrupt the sonic transmissions of submarines. Most of the din is made by a surprisingly insignificant creature, the pistol shrimp. By snapping its claws, it can not only make communication sounds, but something far deadlier. These shrimps are its prey. It deals a knockout blow from a distance by using its claw as a sonic weapon. First, its claw is cocked like a pistol, then fired. The effect is literally stunning. As the claw snaps shut, it fires a blast of bubbles. Incredibly, as the bubbles collapse, they momentarily reach the temperature of the sun. This implosion causes a shock wave that stuns.
Last one, the snapping shrimp.
This is the sound of thousands of snapping shrimp. The snapping shrimp has one normal claw and one oversized so-called snapper claw, which can be closed with lightning speed and produces the snapping sound. The snap is used to communicate with other shrimp and is also used to stun or even kill prey animals. To study the sound production mechanism in snapping shrimp, a shrimp was tethered on a small platform and the sound signal was recorded with a hydrophone. The snapping shrimp was then tickled with a paintbrush and imaged with a high-speed digital video camera. Although it was always thought that the sound was produced by the two claw halves hitting each other, it is seen here that a large bubble is formed. It is the implosion of this cavitation bubble that produces the sound of snapping shrimp. The bubble is formed in a fast water jet squeezed out from between the claws. The water jet velocity is so high that the corresponding pressure drops below the vapor pressure of water and a cavitation bubble is generated which will initially grow in size, then it collapses violently. The high-speed video images and the sound recordings were correlated in time. In this side view, the claw is fully opened. At this position, the claw is fully closed, no sound, while the prominent snap coincides with the bubble collapse. We set up a model based on the Rayleigh-Placid equation to study the bubble dynamics. In this model, a Gaussian pressure drop was used to reproduce the bubble radius as a function of time, as also observed in the experimental high-speed video recordings. From the dynamics of the bubble, the sound pressure curve was calculated. The precursor signal before the loud snap, representing the bubble growth and shrinkage, are also in good agreement with the experimentally determined hydrophone signal. Now that you know that snapping shrimp use cavitation damage to catch their prey, for example this small crab here, you better stay away from the acoustic weapon of snapping shrimp.